Hello, I'm going to talk to you about Cleverscope frequency response analysis, FRA for short. The FRA is useful for a range of things such as amplifier performance, measuring mechanical system performance, measuring the impedance of transformers, inductors and capacitors, measuring the dynamic impedance of power planes, and measuring power supply stability. We're going to focus on power supply stability today. We've got a little power supply and we're going to connect to it a load and measure its performance under changes in load. And then we're going to look at using FRA to do that while the power supply is in circuit powering a real load. To start, we're going to use our Cleverscope scope display to look at what happens to the power supply when we apply a 2.5 amp load. Here we go. I've got a mechanical switch which applies a 2.5 amp load at 5 volts. You can see that this caused a transient in the output voltage. The output voltage has recovered very quickly, but you can see also that there is much more switching activity after the load was applied. The power supply looks stable. I was using a mechanical switch, so this is probably switch bounce in the mechanical switch. Now, one of the issues for us is that it's all very well doing a step change like this on a power supply on its own. But what if the power supply happens to be in a live system? You might not be able to apply 2.5 amp load changes to a power supply in the system. It might already be operating at full load. How do you verify that the power supply is working correctly in the system as it is? That's the whole idea of what the FRA is about. The step response of a second order system, and all of these feedback power supplies tend to be second order systems, is determined by the phase margin. The phase margin is the difference in phase between the stimulus and the response as the gain of the feedback amplifier goes through unity. If this difference in phase was more than 180, then the system would oscillate. Anything less than 180 degrees and we do settle back to the stimulus value. But the rate at which the settling occurs is determined by the margin. So the phase margin is a very good indicator of stability. Here we have a graph taken from a TI application note. This graph shows phase margin versus step response. When the phase margin is close to zero, in other words nearly 180 degrees, the response is very oscillatory. It takes a long time to settle back to the stimulus value. If the phase margin is closer to 50 or 60 degrees, then the step response is very fast settling. If the phase margin is more than about 60 degrees, then it takes a long time to settle, but without oscillation. Let's pull out some of those curves and look at just one at a time to see what it actually means. Again, from the TI document. Here we can see a load step with a phase margin of 45.7 degrees. Instead of recovering directly, there's the startings of a bump. Let's call it bump 1. Here we can see what happens when we make the phase margin worse. With 40 degrees, we see the beginnings of bump 2 forming. It's now taking quite a lot longer for the power supply to recover. When we reduce the phase margin even further to 34 degrees, we get a third bump forming, bump 3. As you can see, the amount of time taken to recover has increased significantly. Our goal is to get a phase margin of about 55 or 56 degrees. It's very hard to measure the phase margin with the power supply because there's so much switching noise that you can't see clear edges and you can't measure the difference between one signal and another very easily. The FRA uses spectral analysis to do this task. Let's look at the structure of a power supply. Up here we have the power stage, which feeds the power through to the unit under test. Here we have the error amplifier, which includes a compensation network, which is used to make sure that the phase margin is optimal. Here we pick off a portion of the output voltage. This is used for feedback. The error amplifier provides an output which is proportional to the difference between the input signal and the reference value. Out here we have the load, which could be resistive and capacitive, and maybe inductive as well. Now, here we have the connection of the frequency response analyzer, which is actually a network analyzer in disguise. This diagram from TI shows a transformer being used to drive the signal across a small value resistor, 20 to 100 ohms, which is connected in the feedback path. Now on the B side here, which is the side that we're going to be measuring the response on, that's a low impedance node. On the A side, which is where we drive the signal into with reference to the low impedance B side, we provide the signal which will be of the order of 10 to 50 millivolts. It may have to be much larger if the gain of this amplifier is high. So, just to recap, we're going to drive a signal across the small resistor, which is small in comparison with the feedback resistor elements, which are usually of the order of 10 to 100 kilo ohms. We're going to measure the voltage, referred to ground, across that resistor. One side, the A channel, will measure the stimulus. The other channel, channel B, will measure the response. And we will be outputting the gain phase relationship between the response to the stimulus. Now we relate the power supply structure, which we discussed a moment ago, with a real power supply. This is based on the TI TPS 55340 EVM. We've got one of these little boards here and we're going to check it out and see how well it performs. So let's look at the various elements of the EVM. First of all, we're going to inject our signal into the feedback path, which is between A and B here, over here between A and B. Here's the output voltage, and it is very low impedance. It's got all these big capacitors here. There's a small value resistor, 50 ohms, which then is in series with the remaining feedback attenuator. The feedback attenuator uses this device to send the difference between the feedback value and the reference value across this opto-isolator to this controller. The controller then controls the switch mode characteristics of the switch and transfers power across this transformer. So this amplifier is composed of the TPS 55340 in collaboration with the optocoupler and the reference. The power stage is also in the TPS 55340. The feedback system here are these components here, and there's a secondary loop, in fact, which goes for AC down here. Anyway, we need to inject the signal across here. Now, in the TI application note, they use the transformer, but we don't need to use a transformer. We can use the CS701. It's isolated, and so it can go directly across any node in the circuit. We attach the ground side of it, which isn't really ground, to the low impedance node, which is this one. We inject the center point of the BNC to this side. We connect channel A to the stimulus side and channel B to the response side. Okay, let's see how this performs in real life. Here's the setup. This is the Cleverscope. It's connected with the two channels to the EVM, which has got a 2 ohm load, and the signal is injected using the CS701 coming out the back. I've got this coming in via a small little cable so it doesn't take up too much room into the injection point. We've connected up the Cleverscope to the EVM and now we're capturing it. As you can see, it's about 5 volts output, and we can see little switch transients which are actually quite significant, about 50 millivolts peak, and this is without a load. Now I'll turn the load on and we can see much more. We can see 300 millivolts of peak noise. Now we can improve the look of the signal by applying the filters, so let's do that. Okay, so now we have a filtered signal and we can see more clearly what's actually going on. Now we're going to start the FRA by turning on the spectrum and FRA control panels. Let's go into View and turn on the spectrum display. let's go into View and turn on the FRA control. Once we have the FRA control there, we don't need to use the control panel anymore. It's all set up using the frequency response analyzer. I'm going to show you how we do that right now. Let's take a look at some of the controls that the frequency response analyzer uses. Up here we have the signal generator setup. We can specify the start frequency, the stop frequency, the amplitude at which the signal generator bottoms out when it's at very low gains, the signal generator offset, which is useful when testing power supplies to check on their impedance at, say, a 3.3 volt offset, the number of steps per decade, the sweep action, which is once or repeated, the sweep amplitude, which is auto or constant. Mostly we use auto because it adaptively finds the correct output amplitude to use to compensate for the gain of the amplifier that's inside the power supply. We can specify a log sweep, and we can use the standard MK suffixes in our units, as in 10 millivolts. This value is a peak-to-peak voltage. The RMS is approximately 2√2 smaller than that. Here's the frequency analysis setup. We can choose the type of transform, RMS amplitude, power, power density, gain and phase, which is what we're doing now, impedance and capacitance and inductance. Down here are the buttons that allow us to do work. We can push the start sweep button to start sweeping. We can observe and change the frequency, and we can clear the graph. Over here are some less used options which you might want to just set up once. We can display the axes in dB or in volts or gain. We can have a log axis or a linear one. We can interpolate the results between points. There may be some use for you to not interpolate and just see single frequency values. We can use a narrowband response or show the entire spectral response. We have an auto setup button. If we click that, then the scope will automatically find the correct amplitude and frequency ranges. We can set the input coupling to DC or AC. The input of the Cleverscope can handle plus or minus 20 volts offset, but if you had to use, say, a 200 volts DC power supply, then you'd set the coupling to AC and live with the frequency response, which goes from about 5 Hz upwards. We can automatically limit the maximum signal that's injected into the unit under test. Here I've set it to a volt. We can also set the maximum bandwidth of the FFT filter that's used to analyze the signal. The smaller the bandwidth, the more sensitive the system is, but it takes longer to run the tests. So there's a trade-off between bandwidth and speed. 100 Hz is a good trade-off value. Down here we have the impedance measurement set up. We can choose the measurement circuit, we can decide what we're going to display, and we can say whether it's series or parallel. Finally, we have the reference impedance for our reference resistor when we're doing impedance measurements. We can plot a gain response by clicking the Start Sweep button. Cleverscope automatically starts the entire system. The SIGGEN output is automatically adapting to the gain of the power supply. Now we are plotting the gain phase response, and you can see it's falling off at 20 dB per decade. As we go up in frequency, the transfer rate increases because we're taking smaller time chunks. The amplitude at the highest frequency is set by the SIGGEN output. We can click on the FRA 0 dB button to show the phase and gain margins. There's the phase margin and the gain margin. The phase margin is about 57 degrees, which is ideal. While we're doing a frequency response, we can inspect the time domain signals just to make sure they're all okay and understand what's going on. We can do this by looking at the scope display, which doesn't need to be used for normal FRA use. Here's the scope display. I'm going to start a sweep again. So you can see here that the signal is increasing at these low frequencies. It's increased to the limit that we specified in the auto amplitude limited, 1 volt in this case. The signal level varies as we go higher in frequency as the gain diminishes. So for small gains we have a small signal. The blue B channel is the power supply output and the red A channel is the stimulus. There we have it. We can do gain phase plots, we can find the phase margin, we can determine if signals are stable and give good transient response, and we can use the time domain graphs to check everything out even while we're doing gain phase plots. Thanks for watching.